afternoon, everyone. Today, my talk is self-sustaining iterated learning, and this is a joint work with Bernard Chazelle from Princeton, and I'm Wang. I was a graduate student of Bernard Chazelle, and now I work at Nokia Bell Labs. So actually, Georgie already mentioned my example here. So this is an experimental psychologist, Frederick Bartlett. He conducted the experiment. So he gave a picture of an owl to a person and want him to reproduce this one. So the second guy, after seeing this owl, he tries his best to draw what he saw and pass this image to a third guy. And then the third guy, this guy is a guy who is not good at drawing. So he draws something like this, and he repeat this process, and later you see that the picture keeps changing, and finally you see, the owl eventually becomes a cat. And it's funny that the tail actually goes from left to right, and we have some reason to explain about it, but yeah. So it's one very funny thing is that so originally his goal is to convey this information about the owl. But later, he found that there's no way to transfer this information. The information is totally lost, and people tend to draw something they like or something they believe what it is like. So later, several researchers, Kalish, Griffiths, and Lindowski from here in Berkeley, they conducted different kinds of experiments. So they try to teach the students some kind of function. So actually, it's a very simple function, just a linear function with negative slope. So the setup is the following. So the student gives you an input x, and the teacher gives a feedback y. So here is 1 point. And later, the student asks about another x, and the teacher gives another y. So after asking a lot of y values for different x values, the student somehow knows what the function is, and then the student becomes a teacher, and he tries to teach what the function looks like to the next guy. And you see that still the shape of the function keeps changing a little bit each time, and eventually the function becomes a line with positive slopes. And they repeat these experiments with different kinds of initial functions, and they found that in most cases, eventually people will end up like this. Yeah. So they don't know, what's going on here, but
name it the cat function.
Yeah. So Kalish and Griffiths, they want to explain this kind of phenomenon, so they build a model. The model is like this. So people are trying to learn some hypothesis from a hypothesis space. And each one, of course, they have a prior belief or prior guessing of what the hypothesis is. And first of all, the teacher has a true hypothesis, and then he used his true hypothesis to generate some kind of data. And you can see here, each hypothesis is associated with a likelihood function that can give you data, according to different distributions. And then this data, for example, it could be 10 different numbers, and this data is passed to the first student. And after seeing this data, the students, use Bayes' rule to update his prior to a posterior pH given data. And then the student becomes a teacher and use this posterior to sample a hypothesis from the hypothesis space, and then use that hypothesis to generate maybe another 10 different data points to the next student. And then they keep doing this. And what they found is that actually this process, the posterior distribution at each time, actually form a Markov chain, a time homogeneous Markov chain. So it will eventually converge to its equilibrium distribution. And the equilibrium distribution turns out to be the prior distribution, which is pretty bad news, because the prior distribution is actually what you already know before the learning session, and your posterior is after your learning session. And this result actually tells you that no matter how hard you keep trying to learn, eventually you will learn nothing but what you already know. So this is pretty bad news for maybe we can think about our education system. So professor teaches the students, and in 20 years, the students become the professor and teach the next generation of students. So here, actually, the result tells you that now it doesn't work. So eventually, you will learn nothing. So the good news here is that so students here may have another excuse to skip class. So what went wrong here? So actually, unlike in most cases, people talk about the how to push the system into equilibrium. Actually, here in such kind of a biological system, actually equilibrium is a very bad thing because equilibrium in biology usually means death. So it's a very bad situation. So here, what we try to do is to prevent this system from falling into the equilibrium. So we made a very slight change here. So instead of transferring constant bits of data in each learning session, actually we kind of increase the amount of information transferred at each step. So, and we want to use this strategy to make sure the system does not fall into the equilibrium. So we need some criteria. So here we make a definition about epsilon delta sustainability, which is pretty standard. So it means that with probability higher than 1 minus epsilon, the distance between the truth and any learner's belief should be very, very small. And actually, we can prove that. So for each learning session, if the number of data here transferred is increased in logarithmic order of t, then actually we can prove that with probability greater than 1 minus epsilon, the hypothesis from the beginning and the hypothesis from any learner should be very, very close to each other. So it's a good thing here. And of course, this iterated learning has some background in language evolution. So here in different words, I can see that. So if there are n different languages and there are totally s different sentences in all these languages, actually, if you use this kind of amount of teaching data, actually you can prevent the original language from decaying to some nonsense. Okay, so here it's a good thing for our education system because as long as you stay in school for more and more years in each generation, eventually you won't, eventually you will be able to learn anything you want. Okay, I think I'm running out of time. So here is the part that I brag we can do more without going into any details. So here, because originally we learned how the hypothesis directly generates some data, but later in this experiment from Griffiths, actually they need both the hypothesis H and some input data X here. So in this case, we can also prove that if you increase the amount of data in each learning session, still you can make sure your original information is sustained with very perfect accuracy. But here you need polynomial order in T because in this case the data point X here is generated randomly, and the hypothesis space is infinite. So actually you need more effort to make sure your system does not go into equilibrium. So eventually you can make sure that the original straight line with negative slopes will be sustained eventually. Okay, that's my talk. Thanks.
Any questions? Yeah. So in your proofs, are you doing this with actual people, or these are mathematical?
A mathematical proof, of course.
I mean, did you actually test this with people?
Actually, we run simulations because all these are randomly sampled and all the data points are just the original one plus some noise. So actually, we can simulate it by computer, and yes, it supports our theories.
But to do that, you have to have a model of people, and it's not clear.
Yeah, because we have the model of how data, for example, here we have the model of how data is generated and how data is learned because we use the Bayes rule. So actually, we have a full set of models for how people learn. So yeah, we can simulate it.
Okay.
Yeah.
Any other questions?
in a model where the learners don't have unbounded patience for the duration of their training as t goes to infinity, I could instead think about having each teacher just teach an increasing number of students each a bounded amount of information. Have you thought about a model where
Oh, right, yeah.
one teacher is passing on bounded amount of information to growing number of students, and then they're doing some kind of majority function or something to stabilize?
Yeah, we do consider about it, and it actually depends on the communication between the same generation of students. So basically, you will assume some kind of protocol of information transfer between them. So if they are totally open to each other, then teaching n students with one bit data and teaching one student with n bits data is the same. Yeah, so in that case, the result should be the same.
One last question here. So just to be clear, so you said that the slope stays the right one. That is a simulation where you somehow model people with.
Here, so this one is an experiment based on actual human.
Okay.
Yeah, and actually there are some students here in UC Berkeley. Because Griffiths is a professor here, so they actually hire a lot of students to do it.
Your experiments where the slope stays the same.
Yeah, that's the computer simulation.
But my question is, suppose that you run the original experiment with your models, would you see the slope changing?
Yeah.
This way?
Yeah. Actually, because the prior is, you have to assume that the prior distribution for the hypothesis is something looks like this.
Okay.
Yeah.
Okay.
Yeah.
Great. Let's thank the speaker again.